Hey everyone, and welcome back to this class, Advanced Convolutional Neural Networks. So let's talk about this course and why it's different from the first convolutional neural networks, which was Deep Learning in Python Part 3. In the previous course, you were introduced to convolution. We had a whole section devoted to just convolution by itself, looking at how it works, looking at some ways to use it for some classical applications. Once we had a good grounding on convolution, we added it to the neural network. That, of course, gives us convolutional neural networks. We saw that these could be used to build much more powerful image classifiers than regular feed-forward nets, because the filters found by backpropagating through convolution lets us look for image features such as differently angled edges and different colors and textures. In short, using convolution allows us to take advantage of the structure of images, whereas a feed-forward net is more general. It assumes nothing about the data, but that makes it less suited for images in particular. The structure of a CNN is such that each layer finds progressively more and more complex features of the input. We looked at how to do both training and inference with a CNN, and we looked at how the same basic architecture of the LeNet has inspired newer architectures such as AlexNet and VGG. This course is way different because I'm already assuming you know what a CNN is and how to build one and train one and use one for image classification. The first thing we're going to look at in this course is a direct follow-up to what we did previously. Now that we have an understanding of the basic CNN architecture, what are some more complex architectures that don't follow the same pattern? What are some of the innovations that have been made in CNN architectures in the past few years? So in this course, we'll be looking at VGG, ResNet, and Inception. These three are the foundation of pretty much every state-of-the-art computer vision system these days. But this isn't just a course about building more and more CNNs. That's just a tiny part of this whole course. The real reason we want to look at these concepts is because understanding them is the key to understanding more complex systems. So what's one huge problem with these state-of-the-art CNNs? One comment I hear a lot is that neural networks take an extremely long time to train, even if you use a GPU. That was the case even in my old course with 3 and 5 layer neural networks. In this course, we'll be looking at 50-layer neural nets. Well, luckily, deep learning researchers these days are committed to openness. And so what is pretty cool about this industry is that we have an unprecedented connection between state-of-the-art research and the average Joe. No such thing exists elsewhere. If you look at finance, biology, medicine, physics, pretty much any other field, they are very hard to get into, and it's pretty much impossible for you to do something like, say, build a state-of-the-art particle accelerator in your bedroom. But deep learning is special. Researchers have done us a great service by sharing their state-of-the-art code and pre-trained neural network weights. In other words, there is pretty much zero training that needs to be done. What I'll show you in this course is something very cool that builds off this idea. This is called transfer learning. What we're going to do is take an existing pre-trained neural network, do some fine-tuning, and make that state-of-the-art neural network work for completely new problems. So for example, you could take a state-of-the-art Inception network and use it on a dataset that it's never seen before. And it takes less time to train than in previous courses because we make use of transfer learning. That is pretty amazing. One thing we didn't get into in the previous CNN course was what are some practical systems that involve CNNs. We touched on this in Deep Learning Part 8, GANs and variational autoencoders. We saw that CNNs can be used not only to classify images, but to generate them too. We created a small system of CNNs involving a discriminator and a generator that work together synergistically to produce very real-looking people that are not actually people. But that was all about unsupervised learning. In this course, we're going back to supervised learning, but looking at much bigger and much more complex systems that involve CNNs. The first of these systems is object detection. We'll be looking at a state-of-the-art algorithm called SSD. SSD is a real milestone in object detection because it is both faster and more accurate than the previous state-of-the-art. This is not just a nice computer science project, but a prerequisite safety requirement to any self-driving vehicle. You can imagine that if cars are going to be driving around safely, they need to be able to recognize all the objects around it, and they need to do it fast. Another application of computer vision, one of the most popular, is style transfer. This is where you take one image, which we call the content, and another image, which we call the style, and we combine them together. The final image has the content of one image, but the style of another. It's as if you hired a painter to paint a skyline, but to do it using the style of Starry Night. You can imagine that this would take a real human painter some time, whereas a neural network can do it within seconds and it looks great. So the main theme of this course is that in previous courses, we looked at what goes inside the neural network, specifically CNNs. In this course, we take one step outward. Now we are outside the neural network, we want to ask, what can we do with these CNNs? What systems can contain neural networks, and how can we use our knowledge about neural networks to make them better? Thanks for listening, and I'll see you in the next lecture.